morning. Let's begin with a quick summary of lecture 25. So today's lecture is going to cover and build on the Whiteson stationary uncorrelated scattering model. We're going to add two more pieces of the jigsaw puzzle, something called the level crossing rate, another one called the average duration of the fade. Again, these are all helping us understand and characterize the wireless channel in a better manner so that we can then use it to our advantage. Looking at several examples through the course, we will also now start talking about channels where there is time dispersion. So up to now we have done the characterization of channels without looking at the delay dimension. Only the time dimension has been done, and that with the LCR and the ADF we will build on complete the picture of the time variation. Then we now move our focus to the delay dimension. So that will give us another type of characterization of the channel, which is helpful for us in fully understanding the channel. And then we look at some additional Fourier transform based insights that we can get from this channel. So, but before that, a quick summary of the points that we have discussed. If we were to look at the time correlation, autocorrelation of the complex channel h of t comma tau, h conjugate t plus delta t comma tau. Notice I am using the same value of tau, assuming that there is no time dispersion, all of the multipath components are arriving at the delay tau. We showed that this is a constant times the zeroth order Bessel function. The argument of the Bessel function very important for us, 2 pi fd times delta t, that is what we have used, and just so that we are comfortable with the visualization, basically we are looking along the dimension, the progression of the blue dots, and we are looking at what is the correlation as the channel varies as a function of time. Okay. Now the key parameters that we derived in the last class by looking at the Bessel function was coherence time. Two expressions for coherence time. This gives us a quantitative measure of how much correlation is there in the channel. One of the correlation measures was to reach a correlation value of 1 by root 2. So basically, if you were looking at a normalized Bessel plot, if this is 1, what is the value at which you reach 1 by root 2, and the corresponding value of the time, this would be a measure of the coherence time. So like that you can also do for a correlation of 0.5. As we mentioned, TC1 is the more commonly used, so 9 by 16 pi fd is a very useful formula for us to remember. We also did the Fourier transform of the autocorrelation function. We are doing the autocorrelation or the Fourier transform with respect to time. So delta t mapping to rho as my Fourier variable, we showed that the Fourier transform pair is given by the expression on the bottom of the slide. So the Bessel function maps to a spectrum, what we call as the Doppler spectrum, which looks like a U shape, and with the it is strictly less than fd, because at fd the spectrum this expression would go to 0. So it is a bounded function. So therefore we get a very steep rise as you go close to fd and minus fd. When you see a spectrum like this, how do you interpret it? What do you make of it when you say that the spectral density is of this shape? Dominant components are close to fd. That's what it says. Basically, because the density is very high for these. So as you go closer to the fd, your strong components. So those are the ones that are going to make the most impact. So given that scenario, we also in the last class towards the end made a statement about the impact of such a channel. So let me just repeat that in case there was some doubt about that. Spectral broadening was the last concept that we touched upon. I'll restate the result, and hopefully that will be a good insight into what we are talking about. So we are going to consider a single tap channel. A single tap channel which has the statistics as we have as described before. So the spectrum of the signal is from minus f0 to f0. The received signal r of t is equal to h of t comma tau s of t minus tau. Okay. So, some delay it happens, but there is only one channel. Notice that this is a multiplicative process. This is where I think there may have been some confusion. So, I am doing multiplication in time. So, if I were to try to interpret this in the frequency domain, I would have to do convolution of the spectra. Multiplication in time corresponds to convolution in frequency. So, therefore, the frequency domain interpretation says convolve this with the spectrum of the channel response, and again from the power spectral density I know that the channel response must be 0 outside of FD. So, the likely shape is something of this type. It is not exactly the same, but it is of that nature. There is a strong spectral components around FD, that is H. So, if I convolve these two, where this one goes from minus FD to plus FD, then the resultant spectrum that we get is a slightly broadened spectrum. So, the original spectrum is here, the broadened spectrum is, this is F naught plus FD, again this is, we have looked at this a couple of times, minus FD. So, basically slightly wider. I believe we have also done the spectral widening as a function of the bandwidth of the signal. So, just as a example, you can please verify that if I were looking at 100 kilometers per hour speed at 900 megahertz, that will fix for me my Doppler frequency, Doppler of 83 hertz. Now, the total broadening of the spectrum is 2 times 83 hertz over a bandwidth. Supposing you are looking at the GSM signal, the bandwidth is 200 kilohertz into 10 power 3 into 100 to get percentage. This comes out to be 0.083%. You may not even notice that the spectrum has become wider. Okay. Again, we have mentioned that the frequency domain interpretation says that the impact is minimal in terms of the spectral broadening. However, so this is the frequency domain impact. Okay. But on the time domain side, the story is different. The channel is varying as a function of Doppler, and therefore, we need to be very aware that the impact that it is going to have on the coherent detection aspects. Time domain, there is channel variation, and that is going to impact our ability to do coherent detection. Okay. So, this will affect coherent detection. Again, the whole idea of the analysis is so that we know how to characterize and handle the impact of the channel. Okay. So, that is the so today's lecture we are going to introduce 2 more characterizations of the channel with the time variations of the channel. So, let me begin by introducing the notation. We are dealing with a fading channel, not dispersive at this point, we are not talking about dispersion. So, h of t comma tau, so basically variations along the tau dimension. So, the characterizations that we have done so far, we would call it as the temporal characterization, anything to do with the time dimension, temporal characterization. And the temporal characterizations that we have done so far are to get the autocorrelation of the time variation. We showed that it is a wide stationary process, does not depend on the time itself, but on the time difference, RH of tau. And if we did a Fourier transform of this, we will get S of rho comma tau. This is the Fourier transform, and the transformation variables are delta t to rho. Okay, that's so far, that's the extent to which we have obtained. So, what we can say is we have a statistical characterization, but now I have to design the system. So, for system design I need something which is of the following form that is very useful for us. So, if I were to focus on the system design aspects, the 2 parameters which we have already referred to in terms of their impact on the system, one is going to be the number of fades per second. So, what are the things that this is going to affect in terms of system design? What would this affect in terms of system design for coherent detection? Well, number of fades per second tells me that I have to send as that many training sequences so that I can estimate the channel, because I assume that every time there is a fade, I lose track of the channel and I need help, the receiver needs help. So this is going to affect the frequency of channel estimation. So how often should I send the training sequence? So frequency of channel estimation for coherent detection. Okay. Now we have already seen what are the things that affect the fades, the number of fades that occur. What are the two? One is Doppler, of course, very good. So the Doppler will be an effect. What is the second one? There's another one which see, it also has to do with how much margin you have, and therefore what constitutes a fade. So there is the notion of, one is Doppler, of course, there is no arguing. The second one is a threshold. What is your threshold for a fade? And this threshold actually depends on the margin that you have built into the system. So in other words, if I were to draw it in terms of a time variation, the channel fluctuates like this. Now if I have designed my system to have this as my threshold, I get a certain number of fades. If I have designed my threshold to be something else, this is a fade, then I get much fewer fades. So what this tells me is, in the second case, the dashed line case, I have more margin, therefore the fades are not occurring as much. So an important element is going to be the threshold that, at which you are going to declare a fade. So one is the number of fades per second. The other very important system design parameter, which we actually talked about it quite extensively in the context of the interleaver, was the average duration of a fade. Once a fade occurs, how long will it last and how many symbols or bits will it affect? So average duration of a fade. Okay. So the acronyms that are used are ADF for average duration of a fade. The number of fades per second is called LCR, or level crossing rate. So if I set my threshold as VTH, how often will I cross that threshold? So that is the understanding of the level crossing rate. So let's just write down the acronyms. Level crossing rate refers to the number of fades per second, and the average duration of a fade is the. So what I would like to do is not go through the complete derivation, but give you enough pointers that you can then pick up and read the proofs that are given to us. So the LCR is the first thing that we will address. Level crossing rate. The original formulation of this, by the way, this is another aspect of the temporal characterization. Let's just write that down. This is also part of the temporal characterization. This also has to deal with the variation with respect to the function t of variable t and not tau. This is variable t. So temporal characterization of fading, this is one more element that we are utilizing, and it basically adds to our understanding of what we already have in terms of the autocorrelation and the Doppler spectrum. So this is a very useful one. So the original formulation was made by a communications engineer by name Rice, the person after whom Ricean fading is given. It's published in the journal called Bell Systems Technical Journal. We have already used this when we introduced the McDonald's paper. That's where a lot of the original work came from, 1948. Archives are present. If you would like to take a look, definitely you should. So basically, Rice posed a problem that looked like a very mathematical problem, but it actually has a very useful systems level interpretation. So the problem that was posed by Rice is, what is the probability that the signal envelope, always we are talking about the envelope here, we are not talking about SNR, signal envelope, which has got, it's a complex Gaussian random process, it's got a Rayleigh statistics, but now we are looking not at the envelope, but we are looking at the envelope of the signal. Probability that the signal envelope lies in an interval which is bounded by V and V plus dV. So a picture may help. So basically the signal is fluctuating, and there is a level which we have identified or we have specified as V, and dV is slightly higher than. So, this is V plus dV. So, what is the probability that the signal lies in this region? So, basically you would look at the time duration for which the signal lies in this interval. So, this would be a part, then again you will see what are those those times that you will have. Okay. Now, keep in mind that this is the fluctuation of the envelope. The fluctuation of the envelope depends on several parameters. So, the slope of this fluctuation is a random process, so therefore I cannot predict. So, the slope can theoretically be positive or negative. If it is increasing, it will be positive. If it is decreasing, it is negative, and it can go all the way from being almost flat, which means very low Doppler, or very high Doppler. Again, instances of both can happen. So, he also bounded the rate of the rate at which it crosses. So, with slope in the range V dot to V dot plus dV dot. Okay. So, some slope, and within that some within a certain margin. So, what is the probability that the signal envelope lies in this region V plus V and V plus delta V, and its slope lies in this range in this range. Okay. And as you would expect, V and V dot are two different things. One is the distribution of the envelope, the other one is the rate of change, and the assumption that Rice made was that they are independent, which is a reasonable assumption. What we know about V is that it is Rayleigh distributed. So, already we know one of the two variables. The second one is what is the distribution that you can assume for V dot, and Rice assumed that it was a Gaussian distributed, but that is secondary. But so basically what he said was the probability that it lies in this range can be given by the joint PDF of V and V dot multiplied by dV by dV dot. Okay. So, based on calculus, so this is the probability that you will lie in this region. Now, if I were to define this as this transition period as delta, this is your time axis, okay, and this is the signal envelope, amplitude of the envelope. So, the slope at which this particular crossing is occurring, this particular crossing, let me highlight it in a different color. So, zoom in on this part. It says that the slope that I am encountering here is dV is the change in amplitude that occurs in the time delta. Okay. So, the problem formulation is clear. There may be other parts where the crossing is happening with a negative slope, somewhere the steep slope, and so the question is what is the probability that the signal level lies in this region, and how do we capitalize on this particular aspect. So, here are the steps that are involved, and again I would encourage you to go through and read by the way the places where you will find this derivation are Mullish chapter 5 and Goldsmith section 3.2. Okay, so please do look up, but most of it is the final result is very important to us, but the method of deriving it is also very important. Okay, so the next step from this formulation is the following. It says what is the time taken, time for a single crossing of from V to V plus delta V, V plus dV with slope V dot. But basically is this asking the same question again, which says the time taken will be delta, that was given by dV by V dot. So, if the probability that it lies in this range is given by this expression, so in 1 second what is the probability that it lies in this? I write this expression for 1 second, and the time taken for a single crossing with this slope V dot is also given. Then the number of times you will cross with this slope. So in 1 second, so just follow this argument, in 1 second the number of crossings of the same interval from v to v plus dv with slope v dot is given by, if this is A, this is B, it is given by A divided by B, which if you write it down, it says it comes out to be v dot P of v comma v dot dv dot. So that is the number of crossings. Now v dot can be positive or negative, and keep in mind that any crossing of a threshold can be positive or negative, a single crossing, or if you could look at it on the other side, it can be. So you do not count it as two crossings, though there are two crossings, you count it as a single, because basically it has crossed the threshold once and it will also come up. So by convention we will take only the positive going crossing, that means you are below the threshold and crossing up, so which means my slope can only be positive. So therefore the number of crossings of the envelope at a value v is given by integral 0 to infinity. Basically the slope can be completely flat or it can go very close to 90 degrees of this parameter v dot P of v comma v dot dv dot. Basically now it is a matter of doing the integral, but the most important thing is this is what is the level crossing rate, NV. Okay. Now let me just give you a minute to sort of assimilate this. The formulation had two steps. One is what is the probability that you lie in a certain range with a certain slope, and then if you are at a given slope, what is the time that it takes for you to cross. Then using those two results you say, okay, how many such crossings can there be within a unit time, and then with all the possible slopes, and that gives me the, because my crossing can be occur at any slope, I do not mind, I just need to know that a crossing has happened and I cross it in the positive direction. Okay, so here are the assumptions made by Rice, seems very reasonable. V and V dot are independent, so that means the joint PDF can be split as a product of the PDFs, are independent. Okay. V is Rayleigh distributed, that is already known to us, is Rayleigh, and V dot again through a argumentation of the likelihood of certain types of crossings, he has made the assumption that this is Gaussian. Okay. Depends on the rate of crossing. So using these assumptions comes a very elegant result, which says that the of course the the number of crossings depends on the threshold. So let us go back and define our threshold. So if the Rayleigh PDF is given by Fv of v by sigma squared e power minus v squared by 2 sigma squared, v greater than or equal to 0, we know that expected value of v squared is equal to 2 sigma squared, that is also this RMS value, V RMS squared. So therefore if I define a normalized value of the threshold, let me call it rho, this is defined as the threshold relative to the RMS value. In other words, we have already seen that that is a measure of the margin that you have. So if my V threshold is what is going to determine my fade, the rho is a normalized parameter, then what Rice showed was the result of that integral that was there in the previous chart is given by a very compact form root 2 pi fd, very good, because higher the Doppler, more frequency, more crossings, and rho e power minus rho squared. So many fades per second was the result shown by Rice. Again, the integration is not difficult, but nevertheless the result is more important, so I have chosen to focus on that. Okay, the expression is very important. Okay. Now this is a function, if you look at it carefully, is a function that will first increase and will then decrease. So therefore you will always useful for us to find where the maximum occurs. Maximum value for maximum value of the number of crossings. Okay, so if you differentiate NV with respect to rho, NV with d rho, and then set it equal to 0, then you should find that the maximum occurs at 1 by root 2. Now, is that a reasonable answer? We need to validate. So, here is the fading channel. If you remember our understanding and description of the RMS value, your likelihood of being below the RMS value is quite high, 60 plus %. So, this is approximately where your RMS value is. Now, if you have the threshold value very small, then you will have very few level crossings. If you have it very high, again you will have fewer level crossings. So, it turns out that if you are somewhere slightly below where VRMS by root 2, that is where you are seeing the maximum level crossings, which is correct because the likelihood of you being below VRMS is much higher, and once you are in that region, you are likely to see lots of level crossings in there. So, it is a reasonable thing, but again it can be validated through experimental verification. Okay. So, this is, so V threshold is equal to VRMS by root 2. That is when you will have the maximum number of crossings. Now, if you have only such a small buffer margin, then you are actually going to be in a fade quite often. So, because basically the number of crossings means the number of fades that are occurring. So, that is not a good point to be in. You must have sufficiently more margin so that you can be robust. So, but that is one useful characterization of the time variation of the system. So, let me just give you a minute to sort of digest that aspect, and then we can pick it up from there and build upon that. So, the understanding of what is the level crossing rate and how it is going to impact, and what sort of insights that we can get from here. The level crossing rate depends on the threshold, depends on the Doppler frequency, both of which we have already, even before we started the discussion, we had already looked at it and understood that impact. Okay, if there are any questions, I can answer them. Otherwise, we move on to the next important aspect of our study. Okay, if we then move to the next concept that is also in the temporal characterization space, it is the average duration of a fade, and you will find that actually this one, maybe the previous one was not as intuitive in its formulation, but this one happens to be very, very intuitive in its formulation. So, the average duration of a fade, this is nothing but the expected value that the signal envelope, expected value of time for which the signal envelope is below a specified threshold is less than VTH. So, that is my fade. How much time I am below that, and that is going to determine the probability that I am in a fade. So, a picture is actually very, very helpful for this one. So, this is the time axis. Notice I have shifted from, there is no tau dimension here, so I am using the x axis as my time dimension. This is the amplitude dimension. Now, supposing this is my VTH, the durations that we are interested in, this is T1, I am in a fade, duration T2, I am in a fade, this happens to be a slightly longer fade, T3, and so on, in a overall duration of uppercase T. Okay. So, here is just a one-step insight that we can get from here. The total duration of a fade, total duration of fades is summation of all the TIs. Duration of fades in T seconds is given by summation over I all the TIs. Basically, you measure each of those, and so now ADF refers to the probability that V is less than or equal to V threshold. So from this figure it's easy for us to write that down. It's summation over I Ti divided by uppercase T. That's event that we are looking at. The event is you're below a certain threshold in a time span of T. But this is a quantity that we already know is the statistically it's a CDF. This is the cumulative distribution function, and we know that, we have a way of characterizing that. So this is nothing but FV, the CDF using V threshold as the parameter. This would be given by 1 minus e power minus V threshold by V RMS whole square. Okay, this is something which we know from the statistics of, and if rho is V threshold by V RMS, this is nothing but 1 minus e power minus rho squared. Now this is the, so if I take 1 second duration of the fade that I am in, so in that 1 second how many fades occurred? I already have the expression for that. So the average duration of a fade says take the total period for which you were in a fade in 1 second, which is given by 1 minus e power minus rho squared, that is a probability, into 1 if you want to take it as 1 second, divided by NV threshold, the number of zero crossings that you will expect for that given V threshold for the Doppler channel that you are looking at. So if you just substitute for the NV from the previous example, this comes out to be e power rho squared minus 1 divided by root 2 pi FD times rho. That is the average duration of a fade. So two expressions that we have that are very useful for us. Again, if there are any questions, basically what we have said is what is the probability that you are below a certain threshold multiplied by time to get the duration in seconds. So then divided by, in that same unit time, how many zero crossings you will are likely to occur, and on average that is going to be your fade duration. So the two expressions that we have, NV threshold is given by root 2 pi FD times rho e power minus rho squared, where rho is given by V threshold by V RMS. The other one is the average duration of a fade, which is given by e power rho squared minus 1 divided by root 2 pi FD times rho. Okay, that is a useful parameter, but maybe let us make it even more relevant and practical. So take an example, slightly different example, carrier frequency of 1.9 gigahertz, just for a change. Look at two speeds, 100 kilometers per hour, 3 kilometers per hour, one is pedestrian, other one is vehicular. The corresponding Dopplers, corresponding Doppler frequencies in this case is 176 hertz, this is 5.3 hertz. The coherence time TC1, if you calculate, this will come out to be 1.02 milliseconds. In this case it is 33.9 milliseconds. Lower Doppler, longer correlation time, very useful for us to keep that picture in mind. Now alongside the coherence time, previously using the coherence time we were making some qualitative arguments about how to do the system design, but now alongside, if you now write down T fade, this comes out to be 0.23 milliseconds. So it says that coherence time is 1 millisecond, but actually if you are in a fade, the duration of that fade is likely to be around 0.23 milliseconds. Likewise, the coherence time at 3 kilometers per hour is 33 to almost 34 milliseconds. The average duration of a fade is 7.6 milliseconds. Okay. So now the design of the interleaver and the FEC needs to take into account probably more closely what is the duration of a fade, average duration of a fade, and then correspondingly work with that. Okay. And always good for us to keep in mind if you are talking about GSM, what's the duration of one time slot? One time slot corresponds to 577 microseconds. Okay. So if a fade occurs, what's the likelihood that you will wipe out the entire slot? Very easy to see. Okay. What will happen if you have a fade at 100 kilometers per hour? The average duration of a fade is 230 microseconds. The duration of a time slot is 577. So likelihood that a part of your slot will survive. Now on the other hand, if you had the lower speed, no chance it will wipe out the entire. Now what happens to the time frame, the 8 time slots? One frame of GSM, because that's when your next time slot is going to come. So one time frame is 4.6 milliseconds. Okay, definitely not affected by the duration of a fade, because the fade would have already have gone. If you are at 3 kilometers per hour, very likely that you may have problems with your next time slot also. Just need to be careful how you design your system, so that then we can build on that appropriately. Okay. Okay, so this is just a simple example how to tie these concepts together. I would now like you to sort of put these two pieces of the jigsaw puzzle also adjacent to it, so that we can now add to our understanding of that. So far the temporal characterization of h of t comma tau has given us sort of four aspects. One is RH of delta t comma tau, S of rho comma tau, the number of level crossings at a given threshold, and the average duration of a fade. So all of these are related to the temporal aspect. All of them are connected to the temporal aspect. Okay. So I want you to now shift your thinking to include the delay dimension. So therefore the following simple exercise. So far we have been looking at just one delay. Now a channel where there is time dispersion, anything. So now if I want to look at at different time instances of time, so basically I will have to look. Let me just quickly draw this so that you can then visualize what we are trying to. Okay. So now if I were to look at it at different instances of time, another snapshot, maybe at this time a snapshot, this channel is negative, this one has become something very large, this one is something small, maybe a third window where once again you are positive, this one has become negative. Some variation, but notice that you are interested in variations in time dimension for the different delays. Let me call this as tau 1, tau 2, tau 3. So this is what we are interested in characterizing. Now of course these taus can also change, but in a reasonable window of time, things are you can assume that taus are remaining steady, and therefore you can do the following analysis. So here is our understanding of this picture. First one, I have h of t comma tau. So for a given tau, that means I am only looking along the time dimension. For a given tau, h of t comma tau is a zero mean complex Gaussian random process, because it's something that has some variation along the time dimension. It's a random process, we don't have control over it, but basically it changes as a function of time. However, there is a correlation, so it is wide sense stationary. So if I forget the delay part and only look along these time dimensions for each of these delays, each of them will look like a random process. So given a tau, h of t comma tau is a zero mean complex Gaussian random process. Okay. For a given t, h of t comma tau basically tells you where the multipath components are arriving, the clusters of multipath components. So this is nothing but a realization of a dispersive channel for a given time. If you take a snapshot, realization of a dispersive channel, There are certain delays, certain gain coefficients, but at the end of the day, it is a realization of a time dispersive channel. Now, very important, if I specify both t and tau, given t and tau, that means I have specified both t and tau. H of t comma tau is complex Gaussian random variable. Basically, it is a sample of a random process. So, is a complex Gaussian random variable. Okay. So, what you, if you now accept this, can you redefine what is the snapshot at a given time? It will be a sequence of random variables. If it's discretized, okay, it will be a sequence of random variables if you were to discretize it. Okay. So, from the time dimension where we have gotten the following 4 characterizations, we are now going to shift over to the delay dimension and see what sort of insights we can get from there. So, let me build on the on this particular element in a very quick and a simple fashion. If you remember, we introduced the notion of interacting objects. So, you have a ellipse and anything that lies within an annular region of the ellipse will arrive at a certain, within the certain time uncertainty window. So, like that there are several of these annular regions that we have. So, we said that all of those that are coming from within a particular annular region can be thought of as a single coefficient. Then, because of my resolution bandwidth, the next block I would see would have a distance of spacing of delta tau. So, this is 0, delta tau, 2 delta tau and so on. So, basically coming in from the different annular regions, and this is from our earlier discussion of what we call as the interacting objects, objects that create the multipath, and because of the multipath then, so basically we are looking at the multipath components causing the different reflections that then eventually give you the different delays. Okay. So, again this is a reuse of the earlier expression. We also at that point in time also said that this time resolution delta tau, which tells me, you know, when I can differentiate between the multipath, is inversely proportional to the bandwidth of the signal. So, this was something that we had already explained and we have understood. Now, I would like to incorporate this concept into our wide sense stationary uncorrelated scattering model in the following fashion. Okay. So, the statement that we can make about this is that the first path is coming from a set of scatterers, let me call it a set of scatterers. This is coming from set B, it is a completely different set of scatterers, B set of scatterers. So, each of these effective multipath components that I can resolve are coming from different set of multipath components, that is why they are coming at different delays, correct. So, and again there is no correlation or link between where the set A is located and where set B is located, except that the distance at which they are located. So, what we are making the following statement is that the IOs, the interacting objects that cause the delay delta t, delta tau, are completely different. It is a non-overlapping set, completely different from the IOs causing the other delays, just 2 times delta tau, 2 delta tau, 3 delta tau and so on, and likewise amongst themselves also they are different. Now, this basically says that whatever happens with the IOs in the region, annular region 1, is not going to affect or does not have any bearing on what happens in the with the IOs. So in other words, what happens with this delta tau does not correlate with what happens with 2 delta tau. So therefore, there is a notion of uncorrelatedness between the IOs. Okay, if one increases, the other one may decrease. There is no correlation that is present. Now, how do you incorporate this particular aspect? Very, very important for us. So, expected value of h of t comma tau naught, h conjugate t plus delta t comma tau naught. This is a result that we have already derived. This is the autocorrelation function with the spacing of delta t being the one that determines it and tau naught being the other parameter. Now comes the important extension that we have. If I do expected value of h of t comma tau 1, h conjugate of t plus delta t and tau 2, what is the result? The result says that if tau 1 and tau 2 are the same, there is a correlation function that we know. It RH delta t comma tau 1 if both are tau. But if they are not the same, there is no correlation between the two, therefore the correlation is 0. So I multiply this by delta of tau 1 minus tau 2. So the correlation exists only if you look across the same delay. If you try to correlate the channel at tau 1 with channel at tau 2, there does not exist any correlation because those two are coming from different sets of interacting objects and therefore no correlation exists between the two. Okay. So this is the Whiteson stationary part. This is the uncorrelated scattering. Uncorrelated scattering is the scattering caused at different delays are uncorrelated with each other. Uncorrelated scattering. Okay. So this together gives us the complete picture of what we have to work with, which is called the WSS US model. WSS comes from the time variation. The uncorrelated scattering comes from the tau dimension. You put both of them together, gives you a complete picture of what we are trying to work with. Okay. So now comes a important part of the study of, so we have finished studying the tau t dimension. Now we are going to study the tau dimension. So at a given time, at a given t snapshot, what is the channel response? What is the channel response? Channel response is h of t comma tau versus tau. I am interested in that. Okay. And this is a well known problem in communications. It is known as channel sounding. Channel sounding, some of the early methods of channel sounding says transmit a pulse, narrow pulse, and see what happens at the output. So at the output, let us say this is what you observed. This says there are 3 copies of the pulse that you transmitted and they are coming with different gains and different delays. So this is the channel response of the system. Okay. Or in other words, you transmit a pulse and don't look for pulses, you look for energy as a function of time. Then what you observe is that there is some power that comes out and eventually the power dies down. Effectively, when you transmit a pulse, you inject some energy or power into the system and then you observe, you put a power measuring device at the other end and as a function of time. So as time goes, the effect of the pulse will decay. So you can think of it as a continuous profile of the power, received power, or you can think of it as a discretized model of this, which is the description in the tau dimension. So what is it that we are interested in? We are going to set delta t equal to 0. So my expectation that I did in that previous graph becomes expected value of h of t comma tau magnitude squared. This is nothing but the autocorrelation function at tau. Okay, so as a function, so basically I am looking for the power as a function of tau. So this is the autocorrelation or RH of tau. This is the this is the discretized version. That's the continuous version. So that's the discretized version. Okay. So now, how do we characterize the channel? Most of our digital communication says give me a discrete time equivalent of the channel. So we will discretize it according to our symbol duration or according to, which is also related to the bandwidth of my transmitted signal. So now you see the link to the digital communications part where it comes saying how do I discretize this channel. Now when is it considered very time dispersive? When is it considered not so time dispersive? How much dispersion is there? Do I need equalization or not? Those are the questions that we will now answer because our study is now going to be in the tau dimension. So h of t comma tau, this is the part that is going to tell me whether equalization is needed or not. This is the part that is going to tell me how fast my channel is changing. So if I have an equalizer, how fast should my adaptation be? Because this is going to be dependent on my Doppler. So what we need in a wireless communication system is an understanding of what is the dispersion, how fast are my channel coefficients changing. There are two dimensions. When you put them together, then you have the complete picture of what the communications receiver is required to do. So we will now take up this portion, the tau portion of it, and characterize and also decide when is it considered a dispersive channel, when is it considered. And of course, just like we did for the t dimension, the Fourier transform may give us some additional insights. So we look at that as well. That we will do in the next lecture. Thank you.